Hi, I'm Jacob Reinhold. In this presentation, I'm going to briefly outline our work creating a causal model of multiple sclerosis in magnetic resonance images. Questions in medicine are usually of the form, does this medicine treat this disease? That is, does this medicine have a significant causal effect on a population? Or would this person improve faster on treatment A or treatment B? That is, does one treatment have a greater causal effect for this individual? But it's hard to answer these questions because of confounding, spurious correlation or association because of a common cause. Confounding can statistically associate completely unrelated factors, as shown in this example relating cheese consumption and people dying from becoming tangled in their bed sheets. Confounding is a problem in machine learning because traditional deep neural networks only learn statistical association between the source and target, which makes it susceptible to confounding. Two examples are shown on the right. In the first example, there's input to the network, a picture of a husky, and the explanation for classifying the image as a husky shows that it's not looking at the husky, but the background, which is snow, a spurious correlation in the training data. A medical image related example is shown below, where a cyclogan learns to remove a tumor in a image-to-image translation task, again, because a spurious correlation in the training data. Often when this behavior is noticed, researchers attempt to correct for the problem with heuristic approaches, for example, adding loss and other penalty terms or using data augmentation. But it's been proven that you need causal assumptions to control for confounders in observational data. One way to do that makes the causal assumptions explicit and transparent is with a causal graphical model called a structural causal model, or an SCM. Formally, an SCM is a tuple containing background variables, which are outside the model, endogenous variables, which are the covariates being explicitly accounted for, a set of functional relationships relating the background and endogenous variables, and a probability distribution over the background variables to account for uncertainty. The SCM defines a generative process which we can intervene upon to ask counterfactuals, which basically is what would have happened if the distributions of the covariates changed. In our work, we define an SCM, which describes a generative process for multiple sclerosis and MRIs. This slide shows our SCM in a graphical representation, only showing the endogenous variables, and as a set of functional relationships relating to background and endogenous variables. The endogenous variables include demographic and disease information, as well as the MR images themselves. Come see our poster or read the paper for details about the covariates that are included. We use normalizing flows and a variational autoencoder for the functions and fit the model with stochastic variational inference. The trained SCM can be used to generate samples, as shown here. The fact that the samples are realistic show that the structure of the SCM is reasonable and that the functional relationships were effectively learned. Here's an example of two counterfactuals. The original image is on the left, a counterfactual where we set ventricle volume to 80 milliliters is in the center, and a counterfactual where we set lesion volume to 0 is on the right. The difference images between the counterfactuals and the original are below. This shows that our SCM can generate high-resolution, detailed, and believable counterfactuals. Evaluating counterfactuals is difficult because we necessarily don't have ground truth to compare against. But to quantitatively assess our counterfactuals, we took 124 MRIs of people with MS, passed them through a lesion segmentation network, and measured these segmented lesion volume. Then we created corresponding counterfactual image volumes where the lesion volume was set to 0 and passed those images through the network. As shown in the plot, the segmented lesion volumes for the counterfactuals drops to 0 as expected. If you would like to find out more, please read our paper and visit our poster on September 29th. Look forward to seeing you there.